Hey kids, welcome to section 4.3 multiplication rules and conditional probability. Today we're going to learn how to find the probability of compound events using the multiplication rules and how to find the conditional probability of an event. So first let's talk about some vocab. When can we use this new multiplication rule? So the multiplication rules can be used to find the probability of two or more events that occur in sequence. So the addition rule that we learned about in the last section was when we had a single event. Now that we have multiple events happening, we are now going to use the multiplication rule. Two events, A and B, are independent events if the fact that A occurs does not affect the probability of B occurring. So if you have two events and the fact that one occurs is not going to influence or change or affect the outcome of another event, those two events are called independent. Now you can find the probability of two independent events that occur in sequence by finding the probability of each of them occurring separately, and then you multiply your answers together. So if I want to find the probability of event A and B happening at the same time, I can find the probability of A, find the probability of B, and then multiply them together, only if the two events are independent. So here's two examples of independent events. The first one is rolling a die and getting a 6, and then rolling a second die and getting a 3. Well, since the numbers are coming from two separate die, they're not going to influence each other unless they're somehow like taped together or there's a string between them when you toss them. They're not going to influence each other. The second example, drawing a card from a deck and getting a queen, replacing it, and drawing a second card and getting a queen. Well, since you put the card back in the deck, you are drawing a second card from the exact same amount that you did the first time. Therefore, you're not influencing it in any way, and it's an independent event. All right, let's see some examples. An urn contains 3 red balls, 2 blue balls, and 5 white balls. A ball is selected and its color is noted. Then it is replaced. Big, big. A second ball is selected and its color noted. Find the probability of each of these. So the first question says selecting 2 blue balls. And the fact that you are putting the ball back into the urn makes a huge difference. And we'll see some examples later where we're going to keep the ball out. So since I'm putting the ball back in, the two events are independent. So I can treat them as separate events. So the probability that the first ball is blue is 2 out of 10. And the probability that the second ball is blue is also 2 out of 10. So I can multiply these together. I can get 4 out of 100, which is 0.040. It's really important that the ball is being placed back in the urn before we pull the second. It's kind of like it's resetting the whole problem. Letter B, selecting 1 blue ball and then 1 white ball. All right, so the probability that the first ball I choose is blue, there are 2 blue balls out of 10. I put the balls back in. This next one I want is going to be a white ball. There are 5 to choose from. I still have 10 left in my urn, so that gives me 10 over 100, which is 1/10. Don't forget that probability is always 3 decimals, so you got to backfill your zeros. Okay, letter C, selecting 1 red ball and then 1 blue ball. Well, there are 3 red balls out of the 10, and I put the ball back in. There are 2 blue balls to choose from out of 10. That gives me 6 out of 100, 0.060. All right, the next example, a coin is flipped and a die is rolled. Find the probability of getting a head on the coin and a 4 on the die. First, make sure you ask yourself, is a flipping coin and a rolling die independent events? The answer is yes. So I can multiply the separate probabilities together. So the probability of getting a head is 1/2. The probability of getting a 4 on the die is 1 over 6. Because there's 1 4 out of 6 sides, multiply them together, I get 1/12. Find the decimal 0.083. Okay, so again, make sure that your two events that you're doing or talking about or experimenting with are independent. If they are, then you can multiply them. If they're not, then we have plan Bs. Okay, next question. A card is drawn from a deck and replaced. Then a second card is drawn. Find the probability of getting a queen and then an ace. Queen and then an ace. Okay, the fact that the card is going back in is a big deal because that means we're resetting the deck when we pick that second card. So the probability that the first card is a queen is 4 out of 52. The probability that the second card is an ace is also 4 out of 52. So I multiply these together, I get 16 over 2,704. Find the decimal 0.006. Remember, to multiply fractions, you multiply the tops, 4 times 4, then you multiply the bottoms, 52 times 52. All right, survey on stress. A Harris poll found that 46% of Americans say they suffer great stress at least once a week. If 3 people are selected at random, find the probability that all 3 will say that they suffer great stress at least once a week. Okay, so 46% say they suffer stress at least once a week. Well, 46%, we need to change that to a decimal, move it 2 spots to the left, the decimal, so that's 0.46. All right, so if I ask 3 people, each of those 3 people can answer yes or no independently of the other people's answers. So each person is its own event. So the probability that the first person I ask suffers great stress at least once a week is 0.46. And the probability that the second person I ask suffers great stress once a week is also 0.46. And the third person is also 0.46. So I can shorten that and say 0.46 to the third power. If I do that, I get 0.097. So remember, each of the people are independent, so each of the people are an event, so I can multiply their probabilities. All right, male color blindness. Approximately 9% of men have a type of color blindness that prevents them from distinguishing between red and green. If 3 men are selected at random, find the probability that all of them will have this type of red-green color blindness. Well, each of the 3 people are independently colorblind from each other, so one is not going to influence another. So the probability that the first person is colorblind is 0.09 times the second person, which is the exact same probability because they're independent, times the third, which is the exact same because it's independent. I can shorten that to say 0.09 to the third power. If I do that, I get 0.001. All right, so it's nice when the events are independent, but when they're not independent, we have a plan B. So when the occurrence of the first event changes the probability of the occurrence of the second event, the 2 events are said to be dependent. So when the outcome or occurrence of the first affects the outcome of the second, those are called dependent events. So here's some examples of dependent events: drawing a card from a deck, not replacing it, and then drawing a second card. So because you are not placing the card back into the deck and resetting the deck, you are affecting the outcome of anything else that happens. Selecting a ball from an urn, not replacing it, and then selecting a second ball, same idea. Third one, being a lifeguard and getting a suntan. Chances are being a lifeguard is going to affect the color of your skin, and so those 2 events are called dependent. Having high grades and getting a scholarship. Chances are the higher your grades, the more a school is going to want you to go to college there, so they're going to offer you more money. So yes, higher grades. better chances of getting a scholarship. And finally, parking in a no parking zone and getting a parking ticket. Chances are, kids, if you park in a no parking zone, someone's going to catch you. You might think they won't, but they will. You'll get a ticket, so don't try it. All right, so within this multiplication rule with dependent events, we have our second multiplication rule. It's called, very excitingly, multiplication rule number 2. It says that the probability of A and B happening is still the probability of A times the probability of B, but we have to assume that A has also happened. This vertical bar means given. So we are still assuming that A and B are different events, but we're taking into consideration that B can only happen if A already has. So we look at some examples. Overqualified workers. So in a recent survey, 33% of the respondents feel that they are overqualified for their present job. Of these, 24% said that they were looking for a new job. If a person is selected at random, find the probability that the person feels that he or she is overqualified and is looking for a new job. Okay, well, I'm going to try to teach this in tree diagrams. Maybe that'll help more. All right, so the people were either 33% overqualified or 67% not overqualified. So this is overqualified and not. And then it says of the 33%, 24% say they were looking for a new job. So I guess that means that there would be 76% not. So if I want to find the probability that a person feels he or she is overqualified and is also looking for a new job, I want this path. So I would take the 0.24 for the 24% and multiply by the 33. So I would take the 24%, 0.24, and I would multiply by the 33%, 0.33. If I do that, I get 0.079. All right, homeowners and automobile insurance. Worldwide Insurance Company found that 53% of the residents of a city had homeowners insurance with the company. Of these clients, 27% also had automobile insurance with the company. If a resident is selected at random, find the probability that the resident has both homeowners and automobile insurance with Worldwide Insurance Company. All right, let's get a starting point. I don't know why I choose a person. Just do. All right, so the very first thing that could happen is you either have 53% have homeowners, which means 47% don't. And then of the 53%, 27% had auto, which means 73% don't. So if I want the probability that the resident has both homeowners and automobile insurance, I would want the homeowners and the automobile. I would want this path right here. So I would take the 0.27 and the 0.53, multiply them together, and you get 0.143. So I think the tree diagram helps you kind of visualize what's going on in the problem, and it allows you to kind of see what numbers you need to multiply together, which path you need to take. All right, selecting colored balls. Box 1 contains 2 red balls and 1 blue ball. Box 2 contains 3 blue balls and 1 red ball. A coin is tossed. If it falls head up, box 1 is selected and a ball is drawn. If it falls tails up, box 2 is selected and a ball is drawn. Find the probability of selecting a red ball. Okay, well, you can start down here. And you can toss a coin and get heads, and you can toss a coin and get tails. Well, you're going to get heads 50% of the time, and you're going to get tails 50% of the time. Now, in the heads box, so the heads box, if it falls heads up, box 1 is selected, and box 1 has 2 red and 1 blue. So 2 red and 1 blue. Box 2 comes from tails. Box 2 has 3 blue and 1 red. Okay, so let's see what the probability is. Well, there are 3 balls here. The probability of getting a red is 67%, and the probability of getting blue is 33%. Because 2 out of 3 and 1 out of 3. Down here, there are 4 total, so it's a 75% chance of getting a blue and a 25% chance of getting a red. So now if I want the probability of getting a red ball, well, here's my red path, and here's another red path. So I need to find those 2 paths separately and then add them together. So I'm going to take 67% and multiply it by 50%. 67 multiplied by 50%. And then I'm going to find the other probabilities path, 50% and 25%. Notice that this problem is combining the addition rule with the multiplication rule. So it's combining section 4.2, which was the adding of the 2 separate events being independent, and then the multiplication rule, which says if they aren't independent, then I need to take into account that the first one is the second one can only happen if the first one does. So you can have a whole bunch of different paths as long as you find your percentages that go with it, and then you're going to add them all up. So this first one, 0.50 and 0.67, that gives you 0.335. Your second product is 0.125. So add them together, 460. So basically you have a 46% chance that you'll get a red ball. Interesting. All right, so tree diagrams might help a lot, especially if you have those funky kind of percentage problems. All right, drawing cards. 3 cards are drawn from an ordinary deck with and without replacement. Find the probability of these events. All right, I need to get 3 jacks with replacement. So that means I'm going to take a card out, put it in, take a card out, put it in, take a card out. All right, I want 3 jacks, so there are 4 jacks out of 52. Then I'm going to put the card back in. I'm going to pick another card. I still have 4 jacks to choose from out of 52. Put it back in. I still have 4 jacks to choose from out of 52. If I multiply this, I get 64 on top with 140,608 on the bottom. That gives me 0.0005. So you do have to round this to get to 0.05 or 0.0005. So you might be wondering why, Yanka, are there 4 decimals here when usually there's only 3? And that's because the next number after I can only round once. So take a look at it on your calculator and see what the decimal comes out to be. All right, if we look at letter B, getting an ace, a 7, and a queen in order without replacement. So that means I'm going to take the card out and I'm going to leave it out before I pick the next one. So the first one is an ace. There are 4 aces out of 52 cards. Now, if I leave that card out, there are now only 51 cards to choose from. There are 4 sevens in the deck. Okay, I leave that card out. There are now 50 cards to choose from. And there are 4 queens to choose from. So I multiply these and I get 64 on top, 132,600 on the bottom. That's going to give me 0.0005. These are small probabilities, very specific picking of cards. Okay, letter C, getting a club, a spade, and a heart in order with replacement. So that means I'm going to take the card out and then put it back in. So the probability that the first card is a club is 13 out of 52. The probability that the second card is a spade is 13 out of 52. The probability that the third one is a heart is also 13 out of 52. So I multiply on top, I get 2,197. On the bottom, I get 140,608. I divide 0.016. So basically 1.6% chance that I would get a club, then a spade, then a heart. Small possibility. If it didn't matter the order, no, the order wouldn't. No, you would. Never mind. Okay, getting 3 clubs without replacement. All right, the probability that the first one is a club is 13 out of 52. Now, if I keep the card out, there are only 51 cards to choose from. And if I already chose a club, there are now only 12 to choose from. Then I keep that card out, draw one more card. I now only have 50 to choose from. Pretend the one I did take out was a club. I now only have 11 left to choose from. So now if I multiply, I get 1,716 on the top, 132,600 on the bottom, and I divide, I get 0.013. Okay. So a little bit more about conditional probability. Sometimes the conditional probability of an event B in relationship to an event A is defined as the probability that B occurs after A has already occurred. So again, these are dependent events that are affecting each other in such a way that they change the outcome. Now, there is a formula for conditional probability. Notice that conditional probability has that given vertical line in it. And also, kids, this formula right here is the same one that we saw earlier. Earlier in the slides, we saw the probability of A and B equals the probability of A times the probability of B given A. Kids, that's the exact same formula that we have up here. They've just chosen to divide each side by the probability of A, and then you have the formula. Notice here in the picture, if I want to find the probability of B given A, that's going to be taking the probability of A and B, which is this middle part, and divide by the probability of A, which is the entire thing. So a box contains black chips and white chips. A person selects 2 chips without replacement. That means that one is going to depend on the outcome of the other. That's a conditional probability. If the probability of selecting a black chip and a white chip is 15 over 56, and the probability of selecting a black chip on the first draw is 3/8, find the probability of selecting the white chip on the second draw, given that the first chip selected was a black chip. All right, so if we want to find the probability of white on the second draw, then I can follow this formula up here because the word given is my conditional keyword. And so I can find the probability of black and white on top. And I can divide it by the probability of a black chip. So I guess this is assuming that A is getting a black chip and that B is getting a white chip. Oh, I guess I could have used B for black. Oh well. Okay, so the probability of getting a black and a white chip at the same time is 15 over 56. And the probability that I get a black chip is 3/8. So when you divide fractions, you might not remember. You keep the top fraction the same. and you multiply by the reciprocal of the denominator. When you do this, you get 120 over 168. So decimal, that's 0.714. So basically it's a 71% chance that you're going to pick a white chip if your first chip was black. All right, we got 2 more slides here. All right, parking tickets. The probability that Sam parks in a no parking zone and gets a parking ticket is 0.06. And the probability that Sam cannot find a legal parking space and has to park in the no parking zone is 0.20. On Tuesday, Sam arrives at school and has to park in a no parking zone. Find the probability that he will get a parking ticket. Okay, so think about it like this. The probability of no parking and a ticket, it says in the problem, is 0.06. And then it says that the probability of no parking is 0.20. They want you to find the probability that you get a ticket given that there is no parking. That's what we're trying to find. So you can think of the no parking as your A and the ticket as your B. So the no parking is your A, and the ticket is your B, and the no parking is your A. So you want to find the probability of B given A. And so you can take the probability of A and B on top and divide by the probability of A on the bottom. So A and B is 0.06. The probability of A is 0.20. Divide and you get 0.300. Okay, survey on women in the military. A recent survey asked 100 people if they thought women in the armed forces should be permitted to participate in combat. The results of the survey are shown. Find these probabilities. So, part A, the respondent answered yes, given that the respondent was a female. So, when you have a problem like this, and essentially over here, kids, your table looks like this. They did the totals for you on the outside. All right, so given that the respondent was a female, anytime you have the word given, that goes in the denominator. And then whatever your, that's kind of like your A. And then the respondent answering yes, that goes in the numerator. And that's like your B. So here you have B given A. So when I go to do my probability, on the bottom, I'm going to put all the females. So there were, let's maybe get rid of this square. There were 50 females. So I could put a 50 in the denominator. Now, of those 50 that I circled, how many answered yes? And the answer is 8. So remember, the given goes on the bottom, and how many of those goes on the top. This gives us 0.160. Okay, let's erase this circle. All right, part B, the respondent was a male, given that the respondent answered no. So your given goes on the bottom of the fraction. That's your A. And then being male is your B. So I guess I can put maybe the A down by like what it is. So female would be A and no would be A. So all my no's would go on the bottom. That's the 18 and the 42. If I add those together, I get 60. And of those 60 that I circled, which ones are male? The answer is 18. That goes on the top. And then I do 18 divided by 60 and I get 0.300. So again, given goes on the bottom, the other goes on the top. All right, last thing that we need to talk about is the probability of doing at least problems. So kids, if you're working with at least, you're looking at a huge calculation that you have to do, depending on how big or how many cards you're drawing or how many die you're rolling, things like that. Anytime you have at least, remember that means greater than or equal to. Greater than or equal to. So if I want, say, greater than 2, I would have to do 2 plus 3 plus 4 plus 5, like all those other ones, but I don't really know when it ends, so I could be infinitely adding. So instead of doing all of the numbers, say, greater than or equal to something, in probability, everything adds up to 1. So I could just subtract whatever is below it, and whatever I would have left is whatever would be greater. So you're kind of like finding the complement, knowing that if it does happen and the probability of not happening, if I add those together, I get 1. So here's an example of that. A person selects 3 cards from an ordinary deck and replaces each card after it is drawn. Find the probability that the person will get at least 1 heart. Okay, so I want to find the probability of getting at least 1 heart. So to do that, I would have to find the probability of getting 1 heart, plus the probability of getting 2 hearts, plus the probability of getting 3 hearts. Well, that would take forever. So that would be, I'm just going to put it 1 heart plus the probability of 2 hearts plus the probability of 3 hearts. Now that's going to take some heavy calculation. Instead of adding up 1, 2, and 3, I could do 1 minus the probability of getting 0 hearts. That's a lot easier. So I'm going to do 1 minus. Now, each card, since I'm putting it back in the deck, each card is going to reset the deck. So the probability that the first one is a heart is 39, or is not a heart, my bad. The probability that the first one is not a heart, or 0 hearts, is 39 out of 52. Since I'm putting that card in, the probability that the next one is not a heart is 39 over 52. And since I put it back in, the probability that the next one is not a heart is 39 out of 52. So basically, I just have to do this calculation, and it is way shorter to subtract away no hearts than it is to add up all the probabilities for 1, 2, and 3. If I do this properly, I get 0.578. So if I draw a card, put it in, draw a card, put it in, draw a card, there's a 58% chance that I'm going to get at least 1 heart. Okay, a coin is tossed 5 times. Find the probability of getting at least 1 tail. Well, the probability of getting at least 1 tail, I could do probability of 1 tail plus probability 2 tails plus 3 plus 4 plus 5, or I could do 1 minus the probability of no tails. So that's 1 minus. Now, each coin toss is independent of another coin toss, so I don't have to worry about any kind of conditional probability. So the probability that the first one is not a tail is 1/2, and the probability the second one is not a tail is 1/2, and the third, and the fourth, and the fifth. Now I could write that a lot nicer and say 1 minus 1/2 to the fifth. If I do this, I get 0.969. Every time you flip the coin, you're going to make it greater and greater and greater. All right, last example. The Neckwear Association of America reported that 3% of ties sold in the United States are bow ties. If 4 customers who purchased a tie are randomly selected, find the probability that at least one purchased a bow tie. So the probability of at least one bow tie equals 1 minus the probability of no bow tie. Telling you the kids that write it out every time do way better at the at least ones. So this would be 1 minus. Well, if 3% do get a bow tie, then 0.97 do not get a bow tie, and there are 4 people. So this gives me 0.115. All right. Well, kids, that's the end of section 4.3. If you guys have any questions, please let me know. And as always, keep calm and keep trucking.